Okay, this video is going to walk you through how to get cyclic voltammetry data that is saved as a text file or a CSV file, get that imported into a proper format in Excel so that we can conduct two different types of analyses. One is evaluate the reversibility, and the other is evaluate the mechanism of electron transfer. And so there's several ways that you can get data into Excel. This is a super important skill to know because almost always you're collecting data from another instrument on another computer, and that data is almost always going to be exported as a text file or a CSV file. And so getting it into the place that you want to conduct that analysis is really important. So I'll show you a few quick ways. The simplest way is to just locate your file as a text file. Say it's this CV ferricyanide. And you literally just drag and drop it. If you have your Excel set up right, depending on the version, whether you're running Mac or Windows, it may just work. It may automatically identify how that data is separated in that notepad file. In this case, it did, and it just said, all right, I've got two files of data, or two pieces of data. The values here, these are my voltages or my potentials, and then the values here, these are my currents, and these currents are in amps, and these voltages are in volts. If for some reason it doesn't work to simply drag and drop, and in fact what you get is one column of data where these two numbers just run together and are separated, then your import needs to be fine-tuned a little bit, in which case you would just select that single column where both of the data are present, and then you would navigate to the Data tab up here, and then on this banner you would choose Text to Columns. This text to columns allows you to manually choose how your data is delimited. And delimited means what is that first value and the second value separated by. In this case, they're likely separated by a tab. Sometimes you'll find data that's comma delimited, where it'll be X value, comma, Y value. Sometimes it'll be a space, etc. So to operate this wizard, you will click Next and then choose how that data is delimited manually, and it will update in real time what the output, the data preview, will be here. When you're finished, you click Finish, and that will separate data that were in one column into two columns based on whatever you chose as the delimiter. Okay, last case is in, again, a blank sheet. If none of this works, or if you'd like to take this separate tack, totally up to you. Again, navigate to Data, and then this section is all about importing or transforming data. So click the From Text or CSV. This will open up a different wizard. Select the file, the text file that you want to use, and then the wizard will look very similar to the one I just showed you, where I will have the columns of data parsed by whatever the delimiter is here, and the computer is going to choose what it thinks the delimiter is, the best one. In this case, it chose tab, and you can see how the data in the notepad file is being separated into two columns based on the tab delimiter. So you can change the delimiter just like you can in the other one if it doesn't default to the one that you want, and then you just click Load. Okay, so once you have your data in the XY format, it's important to label what those columns are. So remember, these values, these are potential, and then in volts, and then current in amps, typically. That's why this is such a small number. So if I wanted to make a cyclic voltammetry plot, just a basic plot of the CV itself, the one that you saw when you collected the data, then you could highlight these data, go to Insert, and then choose Charts, and then remember, we're always choosing scatters because we don't know necessarily what the relationship between those are, so you always plot these as points. First thing we always do is get rid of grid lines and add axis titles, so we'll label these. So we get a plot that looks like this, and so I've labeled current and potential. The problem, there's a couple problems. One is, it's not customary to have an x-axis that bisects the middle, so we're going to want to push that down here. And then second, there are two conventions to plot cyclic voltammetry. Those are either the US convention, which is often more specifically called the Texas convention, or the IUPAC convention. I tend to use the US convention because I was trained by electrochemists that came from the Texas convention, but we should be able to think about both. The difference is actually pretty simple, and it has to do with whether the currents are positive or negative with respect to reduction or oxidation, and whether we plot the more positive potentials on the left, which would be high potentials, or the more positive potentials on the right, which just means the directionality of this axis. So if we look at this right now, what I can tell you is that anytime you're moving in the negative direction in potential, which would be starting here and sweeping this direction, right? We're moving from this value, which is a higher potential, to the left potential. That's whatever wave you see, whatever current you're drawing, that's reduction current. You're doing a reduction on this end at more negative potentials, and the oxidation occurs at more positive potentials. So it turns out the way that this thing is plotted, this is reduction potential, this is oxidation potential, it actually doesn't fit either of these conventions. So we're going to have to modify this to make it fit. If I wanted to convert this to the IUPAC convention, then I would want my reduction potential to be at the lower, more negative potentials, which they are, but I want reduction current to be downward facing, meaning negative currents, and oxidation potentials being positive currents. Whereas right now, my axis is oriented in the correct direction for IUPAC, where I have high potentials on the right, low potentials on the left, but I need this whole thing to flip upside down, which would mean I'd need to multiply my current here by -1, produce a new current, and then replot this data. Okay, so if I do that, I end up with a plot that looks like this. So this would be the IUPAC plot where, if I look at this, the convention is such that high potentials are on the right side of the plot. So the largest, most positive potentials over here, which is what we see. And the reduction current, which is the one that you see when the wave is more negative, that should be pointing down at negative currents, and that's exactly what we see. So we see a picture that looks something like this. The only thing to change now is to get this axis to move all the way to the bottom. To do that, sort of counterintuitively, you want to click on the y-axis here till it's highlighted, and then right-click on it, choose Format Axis, and then what you'll get over here are different options for axis, and you want to change this thing that says horizontal axis crosses. Right now it's crossing at 0. You want it to cross at this minimum value, which conveniently is also included in the bound. So you can just copy this and then paste it in here, and that should fix where this is crossing. Okay, the last thing I'll show you is how to get this into the US or Texas convention, which is almost even easier, because if we look at this, notice that we want reduction current to be positive, which in this case it is, because remember the reduction current is the one that's more negative, the oxidation current is the one more positive. The only difference with this original plot and the US convention plot here is that we want the lowest, most negative potentials to be on the right side of the plot and the high potentials to be on the left. And if you look at our original plot, these are inverted. And so we just need to change the direction over which this is plotted. But we don't need to actually make any modification to any of our column values like we did for the IUPAC, where we had to multiply the current by -1. So to do that, we just need to, just like we did before, but for this x-axis, we need to click on it until it's highlighted, the axis, right-click, choose Format Axis, so we get the Format Axis pane here. We're going to go all the way down here to where it says Values in Reverse Order, and click that box. Notice that flipped them, but it also then flipped where my y-axis is intersecting, which just means that we need to change this vertical axis crosses section to the maximum axis value, which will be all the way over here. And if you do that, now we end up having a plot that looks like this. Notice these plots look identical in shape, but they're not exactly the same thing, because if they're symmetrical, so it's sort of hard to see. But these plots are flipped. Both axes are flipped relative to each other, which makes it confusing. And so as an electrochemist, you want to be really careful how you are representing your data, whether it's IUPAC or Texas. You can tell based on the directionality of this x-axis, but you would need to make sure that if you're grabbing values from different waves that you're doing it for the right thing. Because on one type of convention, the positive wave would be the reduction reaction, but on the IUPAC convention, it would be the opposite direction. It would be the oxidation reaction. Okay, so now I have the original at the top, I have the IUPAC in the middle, and the US and Texas Convention on the bottom. And so I will leave this spreadsheet as a template in this first tab here called CV plotting so that you can input your own data and plot it accordingly, but it'll be up to you to make sure that you're doing this in the correct convention. And it really doesn't matter which convention, unless you're being asked specifically to plot it in US versus IUPAC. You just need to make sure you know which is which, because you will be asked to plot the peak reduction potential or the peak reduction current, etc., and they will be opposites of each other. So just knowing which is important.